So there is a bit of leeway with this just in terms of like artistic ability. It doesn't have to be perfect. But the idea is you're communicating chemistry, you're communicating structure. And the problem with these is if they get a little too wonky, then it becomes unclear what you're actually trying to express. So let me show you an example of that. So here's a good one. Again, I'm not great at these either. I've had a lot of practice over the years, so they come out all right. That's about how I would draw one. So let me show you some not so great ones, and then you can kind of look at yours and see why that might be not so great. So one issue is when they get too skinny and vertical. So let me see if I can do that. So something like this. Okay, I see sometimes a lot of ones that kind of look like that, kind of squished up. The problem with that is, as we're going to see in a minute, we need to make clear the difference between the vertical and the horizontal. And the more squished up stuff gets, the more horizontal starts to look like vertical, and all the lines start to kind of be going up and down, and it's not clear. Those angles aren't clear anymore. Other things that sometimes go wrong here is if stuff gets too tipped. So this is a little exaggerated, but like, I mean, I've seen some weird stuff over the years, but stuff like that, where it just no longer is clear what is up and what is down and what is around the ring and what's going on. So, it's just something that takes practice. Even if you're not great at drawing stuff, you can do this a bunch of times, sit in front of the TV and just with a notepad and just practice drawing them over and over again, and eventually they'll start to look all right. All right, so does everybody have a model built or one that they can look at or something close by? Okay, the next step is to draw the things that are coming off of them. So one interesting thing about cyclohexanes, about cycloalkanes in general, that we did not have with our straight chain alkanes, is suddenly it can become important whether a substituent, a thing that's attached, is on one side of the ring, we can call it the top, or the other side of the ring, which we can call the bottom. So can I borrow somebody's model here? So if you notice, the structure is not planar, it's zigzags, but you can clearly see that some of them are pointing above the ring, if we hold it like this, and some of them are pointing below the ring. And in fact, at every single carbon, you should be able to pick out one substituent that's pointing up and one substituent that's pointing down. It may not be straight up and straight down. Each one will have one that's straight and one that is kind of off to the side, but there should be an up and a down. So for instance, this one here, you can see it, the up one is going straight up. The down one is kind of like down and off to the side. Does everybody see how that looks there? So take a look at your models and convince yourself that every single one has an up and a down. If it doesn't, your ring is probably not quite in the right position. So in this case, it's not in that chair form, so you need to make sure you got the three straight up. All right, before I forget, those of you who just came in with me quizzes. Anybody else? No. So in this form, instead of having the kind of like form like that goes from down to up, over and up like that, this one kind of starts up and goes down and then up again. So one of these corners has to flip down like that. That's the correct format. So there should be an alternating up, down, all the way around. Anybody else having trouble getting their models in the right position? Yeah, so this one, same thing. You want to make sure that, like that one up there, you kind of start down, the corner down, and it goes up, over, and then up again. Down, up, over, up, down, down. So it should be kind of like zigzagged all the way around that. The other way to tell it's the right spot, you have this nice little tripod with 3 straight lines at the bottom. Good. Anybody else having issues getting into position? Okay. So the exam is next Wednesday. You may use these models on this exam. That's not going to be the case for all the exams, but for this first one, you can use the models. So when it comes time to be drawing cyclohexanes and talking about them and thinking about them, it may be helpful to be able to visualize that using the models. All right, so now I looked around. Looks like everybody's got their cyclohexanes in a pretty decent position. So let's talk about the different ways that we express those bonds. So the first way is what we're kind of a little familiar with already, which is if you were looking at this thing from the top, so you set it down on your paper and you're looking at it from the top, we can express it as a hexagon. Like that. Everybody see that your thing looks like that? And then you can express the ones that are coming up toward you with that wedge bond, and the ones that are going back away from you with the dash bond. So each carbon is going to have one position that looks like this and one position that looks like that. And whether we call that hydrogen or whatever else is connected to it, for now we're just dealing with cyclohexane, so let's assume those are hydrogens. And that there's going to be that on each position. Notice looking at your structure that while that describes the basic direction that the thing is pointing, the hydrogen is pointing, it doesn't tell you what the angle is. It doesn't tell you if it's straight up or if it's kind of like sideways and up, or straight down or sideways and down. So this kind of a depiction is fine, but it doesn't tell us geometrically what's really going on in that structure. To do that, we have to draw the chair conformations that we've been practicing. So let's look at what all those substituents look like now from that side view of the chair conformation. So draw a nice chair conformation next to it. Okay. You can see mine's not perfectly even, but it mostly works. So now we're going to draw the substituents, the things that are coming off of it. In this case, we'll say those are hydrogens. To draw those, the easiest ones to draw first are what we call the axial substituents, the ones that are pointing straight up and straight down. So I'll use red. And you can decide if they're going to be up or down by looking at your model, but also by looking at the shape of the chair. If the bonds of the chair kind of make an arrow that's pointing downward, then that axial bond is going to go down. So this one over here, we can see those two blue lines pointing down toward the corner. And so we're going to make an axial bond coming straight down from there. And it should be straight. And that means that the next one over, if you look at your model, if one axial bond is going down, the next carbon on either side has axial bonds going straight up. So they alternate down, up, down, up. Down, up. So the two next to it then are going to go straight up like this. And then the next two are straight down. If you want to be fancy, you can leave a little space to show that it's behind there, but it doesn't really matter. And then the last one is going straight up. And those are called the axial substituents. Straight up and straight down. All right, so then the hardest ones to draw are called the equatorial substituents, which are the ones that are around the sides. And the reason that they're tricky is we have to draw them with the correct angle. Otherwise, it's unclear whether they're supposed to be going up or down. So they need to clearly be going up or down, but also not be straight up or straight down, so that they can be identified as 1, equatorial substituents, and 2, either up or down. So the way you do that is by looking at the nice chair conformation you've already drawn and using the angles of the bonds within that to draw the equatorial substituents. So the one over here on this first carbon to the left looks like this, and let me show you where I got that look from. That particular bond is going to have the same angle, or should if I did it properly, as these other two parallel lines on the structure. This one and this one. So you see how these two are parallel. We talked about drawing the parallel lines in drawing the chair conformation. This one should be parallel to those two. So notice how we constructed that. It's not parallel to either of the ones it's connected directly to. It's parallel to the one past that, the one it's not connected to, the one past the carbon that it's connected to. All right, let's work our way around the ring counterclockwise and draw the rest of those angles and then find their parallels. So this next one here is like that. Does everybody see what bonds that's supposed to be parallel to? So on your drawing, draw it parallel to your own lines. Okay, and the next one like this. Like that. Here. And there. There's also a nice picture of this in your book on page 77, kind of detailing how to make all these angles and what they're parallel to. So if you want something to trace or to look at as another guide, please use that. So you can see now, maybe, hopefully, why it was important to draw those chairs nicely. Because if we drew one of these things like this, and we tried to find these equatorial angles, they would really start to look axial. They would start to look straight because our angles of our chair got too straight. So that's why it's important to, one, have three sets of parallel lines in your chair, and then also to make sure it's not too squished in one way or the other. Okay, so now we're going to flip it and draw the other way. We said that a chair flip is actually an equilibrium type process, so it's something that's going back and forth. It's not like resonance where we just have an average. It's actually flipping back and forth. So you can take the two sides of your model and you can physically flip them. So you can flip the corner that's kind of going down and make it up, and you can flip the corner that's going up and make it down. And we can draw the other chair. Sorry, it's hard to draw on the screens here sometimes. We want to draw the other one with the same nice angles and nice parallelism that we drew the first one. Okay, that's not great. Let's try that again. It should be decent. That one's not great, but it's fair. It'll work. All right, and this time, before I do it, see if you can draw all those bonds, those axial and equatorial substituents on there. Use a pencil or something, or maybe you just do it in one spot and then we'll do it together in the other spot. See if you can get all those angles using the technique that I showed you on the other one. And then I'll show you what the right angles should look like. So it looks like you flip one side and didn't flip the other side. So if you start with this one. That's what you had first, right? Oh, you got the wrong thing in here. That's the square cut. That's a different shape than all the other ones. So you're having like a weird corner. All right, so there was the first one. So then you take one corner and flip it up, and the other side, flip it down, and you should once again have that nice tripod setup. Yeah. Okay, so you set it back to that original spot with one corner down and one corner up. Like that. Flip one up. Flip the other side down.
Okay.
You should once again have those three bonds for you to set up. It is. But that's because nothing's connected to it. It's only the same because nothing is connected to it. If we put a couple red balls on one, you'll see how they do flip from one to the other. We'll do that next. Those chairs are all looking very nice. I'm not just saying that, they are looking nice. All right, so I'm going to draw in, this time I'm going to keep the same color scheme, but rather than making all the axial bonds red and the equatorial ones black, I'm going to actually keep the same ones as they were. So I don't know if you noticed this, but when you flip your model, all the axial bonds became equatorial and all the equatorial ones became axial. That's what happens in this course of that flip. That'll become more clear when we start putting actual stuff on there. But for instance, this, you can't see that, this particular carbon right here, that's the one that actually flips up to become this one. So this one flipped up and became this in the course of that flip. And so that means that this axial bond that was going down is now an equatorial bond that's going down here. The equatorial one is going up, that was going up, is now the axial one going up. Notice what has not changed in the course of that flip is the up versus down, the dash wedge type thing. So in the first example, the equatorial black bond was above the ring, just above the plane of the ring, and now it's straight up, but it's still above that plane. The red bond was axial straight down, and now it's equatorial down. So it's still pointing down underneath the ring, but instead of being straight down, it's like sideways down. All right, so we'll continue the rest of these substituents here. And then the red ones are going to be our equatorial. It should look something like that. Remember that each position needs to have two directions, an up and a down. And it needs to have two different kinds of angles, an axial angle and an equatorial angle.
Are you talking about flipping?
Yeah.
You're talking about this? Or you're talking about this?
Talking about this. It's like rotating the bonds. So that what was down here is now here. Yeah. So when we do the next thing, it's going to become a little bit clearer. So this time, we're going to look at our model with just a couple things attached and talk about why we really have to do it this way. So, here. While I'm putting this together, this is a good time to practice those drawings, check those angles, draw a couple more if you can. is one of those things where it's not so much about how well you understand it as just practicing it. You can understand this very well and still not be able to do it when it comes time for an exam or something. So make sure that you take the time to actually practice drawing all this stuff and convincing yourself what corresponds to what in your drawing. All right, so I'm going to take my cyclohexane and I'm just going to add a couple things to it. If you have all of yours set up already, you're in good shape. Just connect your things the way I do. So on one carbon, whatever carbon, doesn't matter, put two different colored somethings. Something that you can tell apart. Doesn't matter what colors they are or what shapes they are. Something like that. And then I want you to, 2 carbons away from that, put one more on. And maybe leave an empty one too, or leave a blank one. If you still have all your sticks on, just leave them all on the other ones. Something like that. So you've got 2 different things on one, and then 2 carbons away, you've got 2 other different things, whatever they may be. So we're going to try to draw these in a couple different arrangements. So first, we're going to draw them flat, like this. And the way that I have this drawn like that, you can see that if I hold it like this, the red one and this blank one are coming out, so we would call those up. They're pointing out straight at you. And the 2 bluish ones are pointing away this way. So if we were to draw that on paper in a flat way, I would lay this down like this. I would be looking at it from above and say, okay, these 2 are coming out at me. So I'll draw those first. So there's my hexagon that I'm looking at from above. And on this carbon, I have my red thing. And this one, I'm just going to leave it open and call that the blank one. So those are the 2 that are coming out toward me. Again, that's this. If yours is different, you've got different colors, draw what you have. You've got the ones coming out at you. And then the other 2 are coming back behind. I'll call this blue and, what do you call this? Like light blue?
Yes.
Isn't teal more like green though?
It's like aqua.
Aqua? Are we okay with? Let's just call it light blue. Let's not confuse ourselves more. So those are going to be on our dashed bonds. And now we're describing a real physical structure, so we need to make sure things are in the right place. The blue one, which I'll call this one, is on the same carbon as the red. And the light blue one is on the same carbon as this blank stick. So I'm going to make sure to put those in the right place. So we'll say this is our blue one, and this is our light blue one. All right. Those okay, everybody? All right. So now let's try to draw our chair conformation without the model. So we'll put the model aside, and we'll see if we can draw a chair conformation just from looking at that flat structure. So here's how you do it. First step is just draw your chair. Everybody has a favorite direction of which chair they like better than the other one. This one's mine. For some reason, I can always draw it a little bit better than the other one. Although on this screen, it always turns out looking not great. I also have a little lag in my pen for some reason right now, which is not helping. Okay, so we'll say that's our chair. And then the next thing you want to do is just figure out the relationship between the substituents on your ring. So let's start numbering it just like we would to name it. We're going to start at one of these where it has substituents and number around toward the other one. If you look at the last question on your quiz, this is similar to what we would be doing too. You have a structure that's given by a name, in this case 1,1,3-trimethyl cyclohexane, and then you have to draw the two chair conformations and judge their relative stability. So we're basically doing that here with a different structure. All right, so now we can number our chair conformation. Now it doesn't matter how you number the chair conformation because it's blank. We haven't put anything on it yet. So we can pick whichever end we want or whichever thing we want as number one. And as long as we keep the same basic numbering scheme, we should be good. And this one's bothering me, so I'm going to redraw it. I can't draw a great one on here, but I should be able to draw one better than that. It's a little better. All right, so we'll start numbering. I always start on the left corner just because there's no reason to do that. That's just where I start. You start wherever you like. But we're going to number, and we're going to try to keep that same orientation. So if we numbered clockwise, we should number our chair clockwise also. So there's our chair. And we have to draw in the bonds. Now, we have a bunch of hydrogens on here. I'm not too concerned with those. Sometimes it's helpful when you're starting to just draw all the substituents in, just because that's what you've practiced, and that's totally fine. For now, I'm just going to focus on carbons 1 and 3, because those are the only ones that have these substituents coming off. So I'm going to draw both the bonds in for 1 and 3, given my current chair conformation. Okay. And then I'm going to add the substituents. So I see on carbon number 1 that R is up, it's coming out toward me, and B is down, it's going back. And so I'm going to put those on the corresponding bonds. So R is up and B is down. And then on number 3, I have the empty stick going up and the LB, the light blue, going down. Equatorial. If you've kept your numbering right and you've kept your up-down straight, this should be the correct chair conformation for the structure. So let's take a look at our model and see if it does indeed look like what we just drew. And it does. See it? Now, if we had started numbering at a different carbon, we may have made the other conformation, the flipped chair, but we can do that by twisting this anyway. So that's what we're going to do next. All right, so that's one chair conformation. Now let's draw the other chair conformation. And it's not as simple this time as just drawing the other shape and doing the exact same thing, because now we have something that is actually defined, and we have to make sure that we're defining the other one in the same way. So let me show you, that probably makes more sense once we do it. So we're going to start by just drawing the other conformation. Yes? Yeah. Yeah, let's draw it first, and then we'll physically flip it. All right, so when we flip it, we have to pay a little bit of attention of which carbons are flipping to which. So the far left carbon becomes still the far left carbon here, and that's one reason that it's convenient to start your numbering on either the far left or the far right, because then it's easy to find it on both carbons. The other ones can kind of switch positions depending on how you draw it, but the ends are always going to be the ends. So carbon number 1 that was over here is now carbon number 1 right here. And then we still have the rest of them going around clockwise. So we've got 2, 3, 4, 5, and 6, like that. notice 2 and 6 and 3 and 5 kind of like shift their position with the flip, but the ends 1 and 4 stay the same. I mean, they're still on the ends. All right, so once again, we're going to draw in our bonds on numbers 1 and 3. So we've got an axial down and an equatorial up. Number 3, we have an axial down and an equatorial up. We have to be a little bit careful here. This is another reason you want to draw a nice chair conformation so that you can see, so that those corners don't overlap as much as mine do here. They should be a little bit more offset than that, and they'll make the substituents a little clearer. I'm going to get rid of that too. Okay. And then we add our substituents in the way that they have flipped. So on number 1, we have R and B. B is still down, and R is still up. On carbon number 3, the nothing line is still up, and the light blue is still down. So notice that in the course of the chair conformation flipping, up and down do not change. Up and down stay the same. Axial and equatorial change. So the angle changes, but whether the thing is up above the ring or down below the ring does not change. All right, now let's do it physically. So we took our, we got our first structure here, okay? And so what we need to do is take, let's say you take number 1 and number 4, okay? And we're going to flip them. So number 1, which was pointing up, is going to flip down. And number 4, which was kind of pointing down, is going to flip up. So flip one corner. You get this kind of thing, which is called a boat. Flip the other one like that. 1 and 4. So now if I look at 1 and 4, I should have what I drew. Blue axial down and red equatorial up. Light blue axial down and empty stick equatorial up. How's that looking? Got it? All right, so why care about all this stuff? The main reason that we deal with all of this, that we go through all of this, is that when we look at these things in their chair conformations, we can have a better sense of, for some structures, which chair conformation would be more stable. So there's something that we need to define here called steric strain. Steric strain is basically when atoms are forced by a structure to be in each other's way. So because of how a structure is built, some atoms have to get in each other's way. We talked about that a little bit with the Newman projections on Monday, that when we get to that eclipse conformation, if there's large things attached there like CH3s, they get in each other's space, and we have this Pauli strain, which is because of the Pauli exclusion principle. The electrons can't be in the same orbitals, and so they have to kind of like push each other away. They don't want to, they're in a higher energy situation if they're like that. And the same thing happens with cyclohexanes. these axial substituents, if you imagine these as getting bigger and bigger, they get in each other's way. So axial substituents that are 2 carbons away from each other look like little balls, but if you imagine this is like a big CH3 or a tert-butyl group, some like big thing, you can imagine these things getting in each other's way. Whereas the equatorial substituents, you notice, are kind of pointing out from the ring. And so however big that's going to be, it's never going to get in anything's way because it's kind of going off to the outside. So the next term then, which is a type of steric strain, are called 1,3 diaxial interactions, or the book calls them axial-axial interactions. And this is the steric strain that's caused by large axial substituents. So we have something large on the structure, and when it's in an axial position, it's going to have this strain with whatever is 2 carbons away. That's the 1, 3. So 1, 2, 3. So whatever one is 2 carbons away, those things are going to interact with each other. Now, if that group is big enough, even a small hydrogen here is going to be enough to give it those interactions and destabilize it. So generally, when we look at a cyclohexane chair conformation and we want to choose the one that's most stable, we're going to choose the one that puts the bigger groups off on the equatorial positions to get them out of everything else's way. And that's like what's going on in that quiz question. So you look at a molecule, you draw its chair conformations, and then you look at, okay, which chair conformation gets everything out of each other's way. All right, so let's try it. Where's my picture here? Okay, here we go. So I want you to draw both chair conformations for this structure and decide which one is going to be more stable. Try it together or try it on your own. Do what we just did. Try to draw both chair conformations. If you want to use models for this, one thing that's helpful, especially like in an exam where you're a little bit crunched for time, is just pick a color to represent each substituent rather than trying to build that whole thing. Pick a color to represent each substituent, build your model, and then you have something to play with if you need some help seeing it or just checking it. So is anybody brave enough to come draw it on the board? Okay. That's fine. The only thing I would say is that we don't use the wedges on the chair because it's already kind of pretty much. But everything else looks great. Yeah, you can draw them directly, or you can draw it as like a structure. So there's a couple questions for a couple people about that thing that's hanging off the right. Which, how do you describe it? Lisa, like it's hairpiece or something? Yeah. A little hairpiece. So this, if we think about what that is, this is actually, we could describe this as C and then CH3. So there's 3 CH3s coming off of the carbon. That is also known as a tert-butyl group. So you may see that like this, like the book, this is actually a question from the book. They use the term TBU or tert-butyl instead of CCH33. So make sure that you go back. We talked about naming on Monday. Make sure you go back and review some of those different substituents, because sometimes they're not all drawn out, and sometimes it can be really helpful for you to have abbreviations to use in place of those sometimes too. So does anybody want to come draw them? Show us. You've seen my mediocre chair conformations. Who wants to draw some nice ones? Yeah, come on up. You want to draw another one? You got two, so yeah. Uh-oh, you got a bad marker. Yeah, grab another one. Oh wait, need some more markers in this room. That's good. Otherwise I'll get some more. Does that work? All right, what do you think about these? I think they look really nice. So we can see here that in one of the chair conformations, I'm just gonna exaggerate these a little bit so that you can see them. Don't be afraid of your bonds. You can make them long. Okay, so there we've got that, and then if we want to draw the other position, we can. We got to remember that's of course H. I'm not going to take points off if you don't put the H there, but we should remember that for when we start talking about reactions. We need to know what actual thing is there. Same thing with this one. Angle looks great. Let's just make it a little longer. Okay, so something like that. All right, so you can. So let's make some checks here. First of all, are both of these chair conformations are flips of each other, right? See that? This one flips up to become this one flips down to become this one. Are they representations of that structure?
I made a mistake.
Okay.
Okay, so I put the CH3 down.
Yeah.
But it's supposed to be up.
It's supposed to be up, right? So that's true for both of these. Notice that in the structure on the board, the flat structure, we have wedged bonds for both of those. That means that both of those should be on the same side of the ring. They should both be coming out. And that means that in the chair conformation, they're also both going to be coming out. Like that. Both on the same side, both up. I'm actually really glad y'all drew them like that because it's a really common mistake to see the wedges and go, oh, wedges mean up, up means straight, up means axial. That's not how it works. Up means on the up side of the ring, the top side of the ring. Down means underneath, under the bottom side of the ring. So we have one axial and one equatorial. One axial, one equatorial in both of these, but they're both up. They're both above the ring in both cases. If you make the model, you'll see that they're both above the ring in both cases. So between these two, which one is more stable? How would we judge that? Point to this one? This one? First one? Why? Well, let's think about our criteria. How do we judge relative stability of chair conformation? What are we looking for?
Okay, if the molecules are furthest apart, should be equatorial.
Right. We want to minimize those diaxial interactions. We want to minimize large things on axial positions interacting with other things on axial positions. In this case, it's not about these two substituents interacting with each other because they're too far apart. They're all the way across the ring from each other, and they can't both be axial on the same side anyway. What the interactions we're trying to minimize are each of these substituents with the hydrogens on that are 2 carbons away. So this thing is going to be interacting with these guys, and then this one would potentially have interactions with these over here. So then we look at those two and say, okay, in each case, one of our substituents is having these axial interactions with the hydrogens. Which one's going to have the bigger repulsion, the bigger interactions? And the answer is it's going to be the bigger substituent. So this thing being axial is a higher energy, less stable situation than this smaller CH3 group being axial. So this would be the more stable chair conformation because it puts that larger group outside the ring over on the equatorial position. And if we change our angle a little bit here too, right, it's really kind of more like that. It's showing that it's out a little bit. If you were to build this, I don't know if we have time to do it right now, but if you build a tert-butyl group on an axial position, which would be this, and then 3 more CH3s coming off of it, if you actually build all of that, you'll see how much space that takes up and how that can interfere with even just a hydrogen atom on the axial positions too there. So that's how we judge the stability of the chair conformations. Okay, so practice that. The other thing that we should note is when we're naming these, we talked about naming cycloalkanes in general, like going around the ring and finding the positional numbers. There's one more thing you may see in there, and that is that we can use these terms Cysts and Trans. Cis means the same, trans means opposite from. So when we talk about substituents being cis, we're talking about them being on the same side of the ring, and trans opposite side. So that means that these can only apply to two substituents. Two things can be cis or trans from each other. So in this case, how would we describe these two substituents? Would they be cis or trans? So let me be clear on that then. When we say side, we're talking about up-down. So wedges versus dashes. So that these two substituents are both on wedges, which means they're both on the same side of the ring. They're both above the ring. And so that makes them cis. So the name of this compound would be cis 1 tert butyl 4 methyl cyclohexane. So we're expressing there that we have a tert butyl substituent on 1, coming off of 1, a methyl substituent coming off of 4, and that they're both on wedges, making them cis. Yes?
Are they both on the same? Because that H is like down, so isn't it below the ring?
Right, so this H is below the ring.
Oh, so we're just focusing on.
So we're focusing on the substituents,
Okay,
the non-hydrogen substituents. So this one and this one are both above the ring in both cases. So if a trans structure, if we had the same thing, but trans, we would have one of the substituents on a dashed bond instead. So something like that would be trans. If they were both on dashed bonds, that would again be cis, because that's really the same thing just flipped over. That's like taking the model that we made and just flipping the whole thing over. So that's the same structure. Cysts and trans are what we call stereoisomers. That means they're actually different compounds. They're a type of isomers. You would have to disconnect substituents and reconnect them somewhere else to interconvert between them. Yeah.
I thought
You thought the why? Actually, so for our purposes in this class, so you're saying instead of 1 tert butyl 4 methyl, you would go 1 methyl 4 tert butyl. So for our purposes in this class, that's fine. But because we use alphabetical order and that tert is considered not an official part of the name or something, so the B comes before N, M. So that's why they do it that way. Don't worry about it.
the number is on it?
It does, but for naming the structure, you just want to make sure you have the lowest possible numbers and that the alphabetical numbers are, or it goes in alphabetical order. The confusing thing about this one is the tert doesn't count for the alphabetical order. So if it were just butyl, it would be 1 butyl 4 methyl. That would make sense, right? For making, so I should also be clear, that's for naming, the numbers matter because we have to use the lowest numbers and things. If you're just trying to make chair conformations and you don't care about the name, then you can number it however you want, as long as you keep things straight between the chair conformations.
So how would the chair conformation then be different in the trans one? Would it just be which way it's facing?
So yeah, if we wanted to make this into the trans one, instead of the CH3 being up, now the CH3 is down. So the CH3 would be here on this one, and would be here on this one. So the CH3 and the H would be switched. All right, questions? Okay, so this is a really common source of difficulty in this class and in any organic chemistry class. So I encourage you to go look for references that fit for how you like to learn stuff. There's animations online. You can watch other people go through it. You can go back to our videos and look through it. Some people like messing with the models. Other people, it just makes it more confusing and they'd rather just do it on paper. So whatever works for you, just practice this, work on it, and hopefully by next Wednesday, by the exam, we'll have some nice, beautiful chair conformations to draw there. Yeah? Everybody's confident about that, maybe? You can do it. I know you can do it. All right. So let's look, the last bit of Chapter 3 is about physical properties of alkanes. So for our last 10 minutes, we'll just briefly take a look at the physical properties. We'll do this for each type of functional group. So alkanes, of course, well, I don't know about of course. But alkanes come from petroleum, generally. So for oil, we take the oil out of the ground and then separate it into its different components, which are all used for different things. And alkanes are some of the components of natural gas, and they can be purified accordingly. So the major contributor to the physical property of anything, but for now of the alkanes, is the intermolecular forces. Alkanes are nonpolar, as we've discussed. So dispersion forces, or van der Waals forces, or induced dipole forces, they have different names depending on the books you use. I think in Gen Chem here we usually call them dispersion forces or London forces. Those are the forces that dominate their properties. So the dispersion forces are the main intermolecular force in alkanes because they're totally nonpolar. So they don't have hydrogen bonding, they don't have dipoles, there aren't other sources of attraction, so they're just dispersion forces. And do you remember how or what it is that contributes to stronger or weaker dispersion forces? Like what makes dispersion forces in some molecules stronger than others? Yeah, it's how big it is. So the bigger the molecule, the more the electrons can overlap, and the stronger the interactions. So the consequence of this is that the strength of the interactions, the intermolecular forces, depends largely on molecular weight, but also shape. So if you remember from general chemistry, we talked about how something that is more kind of spherical and branched is going to have weaker interactions than something that's long and straight, because something that's long and straight can overlap better. So we're talking about surface area overlap. Big, long, straight, flat things can overlap very well. Little balls only overlap like at certain points. They're going to be a little bit weaker. So if we look at some examples of that, of the effects of this, this is from the book on page 85. All right, so here's your straight chain alkanes. I don't know if you can see those numbers. Make it a little bigger. So your methane, ethane, propane, butane, etc. As you go up by one carbon, you can see a very nice linear increase in the boiling point. Melting point is a little weirder just because solid state interactions have some more stuff going on. But boiling point, there's a very nice, essentially linear increase in boiling point as you get bigger and bigger. So you can see some of our landmarks in temperature there. So pentane with a boiling point of 36 C, That's the first one that's going to be, or the smallest one that's going to be a liquid at room temperature, because room temperature is about 20 to 25 C. Then as you get up to octane, that's where you start getting something that has a higher boiling point than water. Octane is the major component of gasoline. That's what that number means, is the percentage of octane in gasoline. And then as the chains get bigger and bigger and bigger, you actually get things with pretty high boiling points. So that's when you start looking at stuff like waxes, which would be very high molecular weight alkanes and related structures. So in general, these are fairly weak forces, and so they have to get pretty big before they are liquid at room temperature. Also, they continue to be very volatile. So something like octane, which is gasoline, even though it technically has a higher boiling point than water, it's very volatile, which is why gasoline is so dangerous, because the vapor is flammable and it's always producing that vapor when it comes out. Has anybody ever seen like videos of people being irresponsible with gasoline on the internet? You can find them. They exist. Don't do it, because what people think is you light gasoline and it burns, but what actually happens is the liquid doesn't burn at all. It's the vapor that's coming off of the liquid that burns. So even if you have a little puddle of gasoline over there, if you light a match or have a lighter or something, all of a sudden it's going to light everything, including potentially you. So that's why gasoline is very, very dangerous and should not be used to start fires. Lighter fluid is a different type of a structure that is not volatile, and so that liquid will actually burn, but it won't produce a bunch of flammable vapors. So don't light gasoline. It's the PSA for today. All right, so talking about that shape thing. So if we look at two isomers here, hexane and 2,2-dimethylbutane, which is an isomer of hexane, also C6H14. Remember, we made all those isomers of hexane the other day. You can see that the boiling point doesn't change drastically, but it changes pretty significantly, as does the melting point between the different isomers. And that's because of the different types of overlap that those isomers are going to have. So the boiling point is controlled primarily by those intermolecular forces. So the longer and straighter the chain is, the better the overlap and the intermolecular forces. The melting point is also influenced by the shape and the way that it can pack in the solid state. So that one kind of, maybe surprisingly, the lowest melting point is 2-methylpentane, just because that particular shape happens to pack extremely well in a solid, and so you can kind of like fit everything together really nicely. So that makes a really nice solid. So that's basically the physical properties of alkanes. We use them mostly as fuels for burning. So our natural gas coming out of here is primarily methane with some ethane and propane in there as well. We use butane in something like a lighter, right? Propane in a grill, and then the higher order ones, the more liquid ones, as liquid fuels like gasoline. So that's alkanes. Any questions? All right, so obviously your main focus in this chapter is going to be on some of the stuff we've done lately that's a little bit new and tricky. So naming the alkanes, looking at rotations around bonds in Newman projections, and practicing drawing different forms of cyclohexanes. And that will be a major part of the exam, as well as the stuff we talked about in chapter 1, which kind of reviews general chemistry stuff, polarity, Lewis structures, and then drawing the molecules. Good? Okay, so everybody got a quiz, right? All right, I posted the quiz 1 on Blackboard. I will, right now, everybody turn this in, I will post the answers for quiz 2 so you can go through that. And then on Monday, quiz 3 is due, and we'll go through it in class as part of reviewing for the exam. And then on Wednesday is our exam, but the exam is actually during the lab period so that we have that full time. So earlier, the first part of class is a discussion activity. I'm not going to